In this section, we're going to talk about some of the details and subtleties of interpreting coefficients and drawing conclusions. First, let's remind ourselves of the Fuel 2001 data that had income and fuel consumption per capita and some other data values. This is a built-in data set in the ALR3 package. And here on overhead 4, we create some of our new variables that we're going to be using in the analysis. We've seen some of these previously in a previous lecture, but in this overhead we create some new variables and we estimate the model M99 that explains fuel consumption per capita in terms of income per capita, tax rate for gasoline, number of licensed drivers, and log mileage. From our estimated model, we come up with an estimated function that relates fuel consumption to these particular predictors in an expression kind of like this one on the top of overhead number 5. I think the purpose of this overhead is to get you to think about what are the units of a coefficient like negative 6.14. What are the units here? Well, if fuel is measured in gallons per person, and ultimately we have to get back to gallons per person, and this negative 6.14 is being multiplied by a dollars number, that means that this coefficient has dollars in its denominator. This is like gallons per person for every dollar in income is basically what we would interpret these coefficients to be for this in this particular case. The other thing that we want to consider on this next overhead is how to interpret these particular beta hat coefficients. And we've been through this on a previous lecture, but let's just remind ourselves of this, that an intercept is the estimated response, in other words, gallons per person, for states that have zero income, zero gasoline tax, no licensed drivers, and no federal highway miles. That's how we would interpret this fuel consumption figure of 154 gallons per person. We interpret one of these other coefficients, like the income coefficient, as holding the other predictors constant, changing income by 1 unit, $1,000, will decrease fuel consumption per capita by about 6 gallons. And that's how we would interpret coefficients like this. Remembering that when we have a predictor that's measured in a logarithm, in this case a logarithm base 2, increasing log miles by 1 means that we are doubling just miles. So log miles increasing by 1 is the same as doubling miles. And in that case, holding other predictors constant, we get an increase in fuel consumption per person of about 18.5 gallons. If you have different base of logs, you have to interpret them differently. So if a predictor is measured in log base 2, you've seen that what we do is we have to interpret it as doubling the original predictor. If, however, our predictor has been measured in log base 10, that means to interpret a logarithm effect, we basically interpret it by saying that we are going to increase the original predictor value by a factor of 10, not a factor of 2. If we're doing things to log base E, natural logarithms, we are increasing a predictor by a factor of 2.71 roughly. So make sure you use the appropriate interpretation when you do logged predictor values. Because of the ease of interpretation, most of the time we're going to be using logs base 2 in this class. We're going to take a look at a new data set, the Berkeley Guidance Study. There's been a study in Berkeley, California, where Boys and girls have been measured throughout their lifespans, and we have information about their weight at age 2 in kilograms, their height at age 2 in centimeters, both height and weight at age 9, height at age 18 in centimeters. We have some other information too, like the leg circumference in centimeters, their strength at age 9, their leg circumference at age 18, and so forth. And we also have a variable called soma or somatotype, which is on a scale of 1 to 7, kind of a body shape measurement. Higher values meaning more of a pear or round shape, smaller values more of a vertical thin shape. Here is a scatterplot matrix of the Berkeley Guidance Study just for girls, and we're going to be interested in having somatotype be our response variable. You'll see that in this upper left corner here, and we can see the relationship that somatotype has with girls' weights at age 2, when they're at age 9, and when they're at age 18. You'll notice that the response variable has a stronger correlation with weight at later ages. Basically, the somatotype variable is measured when they're age 18. So weight at age 18 is naturally the most correlated with somatotype. You'll notice, however, that the weight variables are all very correlated with each other. Girls that have heavier weight at age 18 tend to have been heavier at age 9. Girls that are lighter at 18 tend to have been lighter at 9, and the same thing is true with the age 2 heights. Not quite as correlated, but it's also true that girls that tended to be heavier at age 2 tended to be heavier at age 18, and so forth. And so there's a very correlated set of interrelationships between these weight variables, and that's going to come to give us trouble in a moment. And here's an illustration of the trouble. We're going to have a model where we're going to use the weight variables to explain somatotype, and take a look at this weight at age 2 variable. Number 1, it's got a negative coefficient, which is very disturbing because we sort of see that heavier weights at age 2 ought to be related to higher values of somatotype. We get a negative coefficient, which implies the opposite kind of relationship, and not only that, it's a fairly small p-value, almost a 0.05 significant p-value. And that is a very disturbing result. It doesn't really make very much sense to us. Try to interpret this. Holding weight at age 9 and weight at age 18 constant, increasing weight at age 2 seems to be associated with a decline in somatotype, and that is just hard to understand and hard to really believe that that's the real effect. Part of the problem with this particular model is that the weight at age 9 and weight at age 18 variables are heavily correlated with weight at age 2. And what we learn about multiple regression is that coefficients of particular terms, like the weight at age 2 term, are heavily affected by what other variables are in the model and how they are intercorrelated with them, and making very strange X transpose X inverse patterns in the estimating matrix. And so in this particular overhead 12, I'm making a couple of new variables out of our weight variables. I'm making a difference variable between the weight at age 9 and age 2, and another difference variable between the weight at age 18 and the weight at age 9. And you can see the scatter plots of these two weight variables are much less correlated with each other. The difference between 9 and 2 and the difference between 18 and 9 are almost not correlated at all. And you'll also see that these variables are not quite as correlated with weight at age 2 either. And this is going to have important ramifications in our model number 2, where I include a weight at age 2 variable and then these increments of change. How much did the girls grow between age 2 and 9, and how much did they grow between 9 and 18, these difference variables. You'll notice on our model coefficients we still have a negative weight at age 2 coefficient, but it is very not significant, very large p-value, and this is really not significantly different from a coefficient of 0. And you can see that the difference variables are very significant and very positive, meaning that if you have an increase in weight, a 1 more kilogram increase in weight between, say, age 19 and age 18 and age 9, you get an increase of about 0.05 somatotype points. A 1 kilogram change increase in the change between 9 and age 2 gives you a 0.1 somatotype increase, and these are quite significant. So we get kind of an improved ability to understand the coefficients and to believe the coefficients have meaning when the predictors are not quite so correlated with each other. Notice we have the same basic information. The R squared is 0.5658 for this model with this arrangement of predictors, and it's exactly the same, 5658, on the original raw weight predictors. But interpretation has been improved, teaching the lesson that the interpretation of coefficients is very heavily dependent on the predictors that are already in the model. Let's take a look for a moment at Model 3, where we have all of the original weight variables and the difference variables in the model at once. And you can see that when we look at the model output, you'll see that R was not able to estimate all of the coefficients. The space spanned by these predictors is really only dimension 3, and these additional predictors are creating redundancies, and there really isn't a way to uniquely estimate all of the coefficients. So in your output in your future, if you see coefficients that are not able to be estimated, it means you have over-determined the system, and you are trying to estimate more coefficients than can be estimated by the richness of the predictor set. And in this overhead we give the summary of the things we've just talked about. Fourth bullet suggests noticing that all of these models have the same residual sums of squares. They are essentially estimating the same kind of thing, just in different ways and in more advantageous ways, in particular for Model 2. I want to give you some idea about what happens if we would drop a predictor variable from a model when it's really needed. So, for example, let's suppose that the data generating system really does depend on x1 and x2 through the mean function that's given up here. And let's just think about ignoring x2. What happens if you just study the mean function with respect to x1? Well, what happens is that mean function, if there's interrelationships between x1 and x2, the mean function for x1 is going to have involvement and carryover from how x2 interrelates to x1. So if the data system really does depend on x2 and you go and you ignore it, you are going to get a slightly modified mean function. The x1 mean function is going to have involvement from x2 in it. And so this is an important illustration of caution for making sure that you have a model that is sufficiently rich and has all of the predictor variables that you need in it, because trying to just have a smaller one might not really give the true picture about what the impact is of x1. Here's just a review about what the impact is of a particular predictor variable x. If the model mean function is beta naught plus beta 1 times x, and you study how the mean function changes when x changes by 1 unit, well, the mean function changes by beta 1. Let's suppose we have a mean function that is involving the logarithm of x. Well, if you change x, how does the mean function change? Well, the mean function changes in a complicated way. It changes as a function of the value of x. So for certain values of x, the mean function changes more than it does for others. And that's an important thing to know about the behavior of the log function. If the mean function for the logarithm of the response variable is a linear function, beta naught plus beta 1 times x, how does the mean function of just y change? And you'll see it's this complicated multiplicative function involving terms beta 1 and x, and also beta naught. If you want to study how this mean function changes, it changes as a function of beta 1, but beta 1 multiplying by the overall level of the mean value of y. And so what does a change in x do to the mean function? Well, it depends. It's different. It's different depending on what the overall level of the response, typical level of the response is. If the typical level of the response is big, you get a much bigger change in the mean function. It's a multiplicative change. Another issue to be aware of is that you need to pay attention to whether the study and the data set that you're working with has been the result of an experiment or whether it's been an observational study. When you construct multiple regression models from observational studies, for example, in the gasoline consumption data from the United States, unless the tax rate has really been changed in a controlled experimental way, it's really not quite reliable to say that when we change the tax rate in a real situation, it will have the impact like the beta hat for the tax coefficient. You actually need to change the tax rate in order to really have causal inference. A word of warning about observational studies, like what we've been talking about. Observational studies can often have lurking variables, and a lurking variable is a predictor that hasn't been included in the mean function, but it's correlated with terms and predictors in the mean function. So take as an example an extra variable that's not in our model, but it's positively correlated with one of our predictors, x. Well, a lurking variable, a variable that has not been controlled in the observational study, may artificially masquerade itself through the correlated variable that is in our model, x, and make it look like x is an important predictor and give us an incorrect inference. Remember, the lurking variable is related to the response, and the lurking variable is related to this poor predictor x, which has just happened to be in our model, and because of the correlation between the lurking and the x, it's going to make it look like our x is significant and important part of the response function, and we make an incorrect decision. The opposite thing can happen as well. You can have a lurking variable that may hide an effect of x that is really there, but the lurking variable may conceal it by muddying up the waters. So the big word of warning on observational studies is to think carefully about what the lurking variables are and what their impacts might be before you try to generalize results, and probably not even think about any kind of causal relationships that are going on from an observational study. There's a little bit more material here about R squared. First thing to notice about R squared is that R squared is very sensitive to the sampling that has been done to create and generate the data. So if sampling has been created with wide dispersion on the predictor values, you'll get an artificially high R squared because of it. So please be aware that R squared is affected a lot by the values of the predictors. And you might be able to artificially get R squared to go up or down just from the data collection. In a simple regression problem, the relationship between the response and the predictor is quite easy. You can just use a scatter plot of y against x. But in a multiple regression model, it's really hard to fully understand the strength of the relationship between the response and our predictor set. What we do to get some kind of graphical display is to plot the observed y values on the vertical axis and the predicted values of y on the horizontal axis. And the correlation from that summary is in fact, well, the square of the correlation from that summary is R squared. And so you can visualize R squared with a plot. And in this particular overhead, you can see that we have a regression model using the weight values to estimate somatotype. And if you plot somatotype against our predicted values, you can see a fairly strong visual representation suggesting that this set of predictors is a pretty strong predictor of somatotype, and that we have a reasonably strong model, but certainly not perfect. There's a lot of the variation in here that has not been explained. But this would give you a visualization of the R squared of about 0.51 or whatever it was. This single graph would let you summarize the strength of the multiple regression model. Sometimes we can have missing values on some of our predictors, and there's typically a couple things that get done when we have missing data. One thing we can do is just eliminate observations in cases that have any predictors that are missing. Another thing that we can do is create some additional data sets that have artificially imputed or guessed values for the missing data. So in other words, let's say predictor X1 is got a missing value on the third observation. What we could do is we could do something like plug in the average for that variable, and that would be a way to be able to use the whole observation even if just a portion of it is missing. And so there are some very sophisticated imputation techniques to be able to use full data sets. Another technique that we should know about is a technique called the bootstrap. And instead of using t-statistics and standard errors for making confidence intervals or making test statistics, sometimes what we can do is we can resample the raw data and build new regression models from subsets of the original data and come up with estimates from each of the randomly drawn subset models, and use a collection of estimates from these randomly generated subset models for inference instead of the usual ways that we do things with R. I want you to be aware of the bootstrap technique. You can read about it in the textbook and also online. I just want you to know it's an alternative way for getting confidence intervals and tests that in some cases work just about as well as the t confidence intervals and the t test statistics that we learn about in this class.